Okay, yes, to continue. Then we next will analyze the space class. Okay. Yeah, unlike last semester, then we try to teach this first so that you have a better idea about structural analysis of the space class. Okay, we previously learned about 2D truss, but in reality, nothing is really 2D. Most are 3D structures. It could possible that they are regular truss from 2D view, okay, but reality that it could possibly have a 3D structure. Okay, there are 3D structure. They can come in various forms, but one of the simplest one is this tetrahedron. They have the four surface. Okay. This kind of surface feature with a very lightweight was first used in the tetrahedron kinds for area structure. So they are stable. They have the 6 elements and 4 joints. So let's count. If you have 1, 2, 3 for the top structure, and then the projected base, they have another 3 trunks. They can combine to make the tetrahedron. Okay, let's have a look how this structure take out. Okay. Okay, let's see. Let's search for internet. Next, how to make the structure. Okay, I think to many of you, you might think this is a tough one. How can you take fly? One simple analogy is, okay, as a kid, how do you draw a bird? Okay. Is something the easiest way of drawing a bird? Projected view. But how do you see the bird in bird wing in 2D view, in an isometric view? Yeah. It could be more detailed, something like that. Okay? But even the simplest simplification doesn't defeat the function. So you can see that with the 2 surface. Okay? So in this case, so they are using the tetrahedron to make the structure to support the kite. Let's see how the mechanism of this kite can be. start with something. First is the 2D one. We already know this line. This is X, this is Y. How about an extension to the Z direction? Okay, Z. Okay? So if you now, if it's rotated, okay, this is X connected to Y, okay, this is the length, okay. So now if you now rotate this, okay, this could be rotated. Then the physical line here, depending how you see. If you see from the base, this is your Z, and this is your X. Okay? And you see from, depending how you do the projections. Because of the rotations, your new projections in the XY plane will appear this dash line. This is again there. If you now project to the YZ plane, this will be somewhere along this line. Okay. And how do you do the calculation of the actual length? Okay. So for this line, we calculated before, this is what we call x squared plus y squared. For this green line, you can calculate this is what we call z squared plus y squared. Okay? No matter how you do. Okay? This line is a 90-degree projection of the line here. So if I draw this, this is a 90-degree projection to the length. Okay. So if this dash line has a projected width of x squared or x squared plus y squared, and this is z, and this expression is now, you apply Pythagorean theorem second time, then you are able to write the full length. Full length is x squared plus y squared plus z squared. The same line can be also obtained if you draw from this triangle. Okay. How this triangle is? This is the dash line. This is the full solid line. This is the base. Base has a length z, and this projected line has a length. What's that? Sorry, this one z. This is x. Y squared plus z squared. So now the length becomes equal to y squared plus z squared plus x squared. Base. 各位看到吗？就是通过这样的方式，我们就可以找到三维上的那个长度。 Okay, with this, then yeah, we confirm the length of the truss in the space is going to be solved by Pythagoras theorem. Okay, so this is a 3D extension. Okay, next, what about the angle? Okay, so you can see, you can define the angle to be the angle between the x-axis to the length. Okay, so this is can be obtained as a cosine angle. Okay, of course you can also obtain the cosine angle from the length to from the z direction to the length direction. Likewise, you can have the cosine angle from the y-axis. So you are not sure what we are talking about, then let's take this broomstick. Okay. So if I restrain the base of the broomstick, okay, this is the reference angle. Okay, if it's only allowed to do one axis rotations, how to define cosine angle? It must be the projected length, okay, which is lower. Projected length. Define the projected length. Projected length must be from the stick tip to my vertical axis. Okay, it's projected from there to here. Okay, so this projected length divided by the full length will define the cosine angle. Okay, yeah, it is 90 degree. Yeah, this is 90 degree. Okay, it's almost zero projected length. Okay. However, if it's 0 degree, okay, this cosine angle 0, then the length is full length. So this is the way how you define the cosine angle. Okay, and then next the question here is, you might have view from 90 degree, okay, perpendicular to the stick. So you see the full length. Okay, but what happens if I now turn my axis of rotation? Okay, if I turn my axis of rotations, okay, you see, it is still the same cosine angle with reference to me. Okay, but from what you see, you almost see completely different projected length. Okay, so when you define the cosine angle, that's why you got to refer to the right axis. Okay. The other way of seeing this is, if I'm lying down and I see this cosine angle, that is going to be completely different. Okay, when I stand up, I see one projected length. But if I'm lying down, okay, then you see another. So no matter how you are, if you define one axis, either axis X or axis Y, axis Z, okay, then they must be perpendicular. Okay, if this is not clear to you, then let's draw out. convention. You have the x-axis, you have the z-axis, and your y-axis. Okay? Let's say this is your x, this is your y. Okay? And then next, you have your z. Okay? So from here, you define a line. In this case, your line is starting from origin. Yeah. So in this 3D space, you can probably not too good. Okay, anyway, just this. Okay, if you cannot see clearly, then let's draw this into a cuboid. Okay, cuboid. Okay, then you have your y-axis, then you have your x-axis. So if this is the box, okay, yeah, if this is the box, then will you be able to find what is your angle, projected angle? Okay. So just now we talked about these. This could be resolved into a few areas. The first area you can take off, let's say, with respect to the Okay, we talked about this one. Okay, it's a projection to. This line is there, it's projected there. Okay. So here just now we define this 90 degree. Let's see. We say 90 degree when this is okay, I think it's different from just now drawing. Okay. If you are drawing, it is 90 degree to the z-axis. Sorry, no, this side. Okay, z-axis is 90 to xy plane. So you see here, the dashed line is the one being perpendicular to 90 degree. You get it? But this 3D line, okay, it's not 90 degree to either axis. Okay, then we'll have a projection. As we do this. This is projected into this direction. Then you got this small length. Okay, length in the x direction divided by the full length is giving you the cosine theta x. Okay, and if you do the projection into this z axis, you have the LZ. Okay, you would probably project it somewhere here. This is your LZ divided by length, and this is your cosine theta z. Likewise, you can do the same, and then eventually you define all three angles. Okay, this is how you define the cosine angle. Okay, in our conventions, just now we just simply take this as full z. Okay, because we take the starting point of the origin. Okay, this is ux. Okay, but if you happen that the origin is non-zero, then you got to do the subtraction. So in this way, you define your 3 cosine angle. Okay, we're going to have the this is what we call directional cosine. Okay. Okay, the directional cosine is still defined the same as we did for 2D case. Okay, this is a projected length in the x-axis divided by full length. This is directional cosine of x. If you replace the difference of the starting and ending point in the x-axis, then you have directional cosine z. If you replace it with the projected distance in the y-axis, then you have the directional cosine y. So you see here, so these are the 3 directional cosine. Okay. In terms, by calculation, it's very simple. So long as you know the two not 1 coordinate, not 2 coordinate, the directional cosines can be calculated using this simple formula without really seeing geometry. Okay. And then next, how about the displacement field? Yeah, we learned about the displacement got to be projected into the length direction. Okay, but that's really difficult. Okay, so what's the issue here? Okay, you know in your global coordinate, you have your x, y, z. Your displacement on each node can be expressed parallel to the global coordinate. You have your u, v, w. Okay. But now, to handle the thrust, the force along the thrust, okay, you can't use the global coordinate. You have to project the global coordinate, global displacement, to the axial coordinate. Okay? So we could possibly have the axial coordinate defined along the x direction, along the I direction, and then other orthogonal coordinates are then the j prime and k prime. Okay, but one thing we know is you can always have the projection, you can always have the directional cosine to give you the answer. Let's see here. If I'm not sure what you're talking about, let's come back to this slide a bit. Okay, x, we might have defined this as the distance. Okay? But you can define a direction angle to be I. Okay. This is a direction cosine of x. Okay? And then how about y? You can define the direction cosine of y to be j. And this direction cosine is k. So what's the feature here? They all are unit vector. Okay? Because of this nature, then you know something about the directional cosine. I dot j is equal to 0. I dot view it from the vector plot, I think this is very clear cut. Okay. Then what are they? They are cosine theta. Okay. A projection to one of the axis. That's it. In the I direction, in the X direction. That's how you define. That was 2D. If you now do the extension, I cos K is also 0. Okay, if they are parallel, but the full expression is going to be cosine. Okay, yeah. Now if you want to define the unit vector for the truss, so what is the direction of the truss? The truss direction, if I write this, this is the xi plus yj plus zk. Okay, this is my direction cosine of the truss. Okay. So in a way, if I now do the redefinition of the coordinate, it is possible to define axial coordinate to be my B vector, okay? But since it's axial, I would prefer using it to be I, okay? I prime, okay? And perpendicular to this, I could define a plane of perpendicular to the axial axis. This could then define, depending on what you like, to define this is the new K prime. And this could be your new, what do you have? IJ, okay. IJ, yeah, but you must fulfill the orthogonality. If your J is defined with this direction, okay, then your Z will be in this direction. Okay, you must fulfill the first hand rule. What is first hand rule? Here the right hand, turn your finger, okay, to define a plane. Okay, and then the thumb pointed direction is then the Z direction. Yeah. So first hand rule. Finger pointed to the axial direction. Finger curl, then this is the first perpendicular direction, Y. And then next, yeah, thumb up, then this define your Z direction. Yeah. So with this, then we define a new orientation, but along the axis. Okay, so you understand what it means now? Yeah. Okay, take for example, yeah, this stick is fixed in length, but if this stick is actually compressible, okay, I take it, if it's aligned vertically, and then I compress. Okay. Yeah, if you cannot imagine what compression means, then let's take an example. Okay, you do the bicycle pump, isn't it? You do the pumping of bicycle. Then you have the cylinder. You press it. Then the stick comes down together with the piston. Okay? So you do pumping. Yeah. if you are upright pumping will give you, let's say, displacement U. Okay? What happens if you are not stable, you lean more, okay? You lean more, you do pumping. This will still give you a U. Okay? But the U here is angle from the vertical axis. Then the question, what you see is the U prime. That is really along the axis. But what I see along the vertical line, okay, is becoming less than U prime. How much is that reduction? You have to do the calculation, okay, by projection. Okay, very simple way of operating this identity. Anyway, the total displacement is the same. Okay, so if I squat and stand up, my total displacement is the same. Okay, but if I now orientate 90 degrees, okay, I lie down and do this same exercise, the displacement will be the same if I am sitting on the slider or lying on the slider. Okay, but from the viewpoint of view, this might appear to be total different displacement. How do I get the total displacement according to my body axis? Okay, one way of doing that is, okay, this one is by projection, it's not by body axis. Okay, so if you want to find the projection in the body axis, you have to take the absolute displacement in the 3D space. So this is the displacement along x-axis, this is vertical displacement, this is depth displacement. If I want to find the displacement along the axis of the bicycle pump, okay, then I have to multiply both sides with the directional axis of the bicycle pump, I prime. Okay? And then this operation will tell you, in the end, so long as you projected the displacement in the x direction into the axis, and you projected the vertical displacement to the axis, you projected the depth displacement into the axis, you finally find the total displacement along the axis. With these operations, basically have the axis displacement equal to the projection of x, y, and z displacement. Okay? So my mathematics is now appear to be simple and uniform to operate. Okay? Yeah. You can do the same for not one displacement. You can do the same for not two displacement. And now your axial displacement can now be expressed as cosine or so-called the directional transformation matrix. Okay? So just now you may have to handle sine and cosine. Here all appear to be cosine, but the angle are different. The angle is a projection angle, the x-axis projection angle into the y-axis and projection angle into the z-axis. Okay, now the expressions is now uniform. Okay, everything, the rotation matrix are all expressed as a cosine angle, but angle are different. Okay, likewise, how to handle the force? Okay, for the force, you can express the global forces in terms of the local axial forces. Okay, but likewise, you can do the same projection. Your local forces is a projection of the global forces. Okay. Now the force vector can be also expressed as the axial forces can be expressed as a transformation of global forces. This remains the same, isn't it? For the same element, they only can take up the tension. Okay? So the element stiffness times the axial displacement vector is equal to the axial tension. So this remains the same, nothing different. But now the re-expression of the axial displacement can lead to this expression in terms of the global displacement. U in the x direction, V in the y direction, and W in the z direction. The right hand side is the axial tension. Okay? And then next, you can write pre-multiplication of the expression here. You pre-multiply these expressions into the pre-multiplication of the rotational matrix transpose will give you the right hand side. This right hand side is going to give you an identity matrix. Okay? So you know the local force was previously the transpose of transformation matrix and force. But now you pre-multiplied it, what you're going to have. Okay. So okay. Let me write this. we learned about a spring element is having two degree of freedom subjected two forces. Okay. The forces can be related to the displacement using this stiffness matrix. Okay, so this is what we learned. This is 1D, and for 2D, if your spring is oriented into this direction. Okay. The axial displacement is still U2, U1. But now the coordinate you are using is giving a big U1, big U1. Okay, then your matrix is going to be transformed. Okay, so previously we learned about these transformations. It is your stiffness matrix being transformed. Then this will then the global displacement vector times transformation of these local forces